Hey everyone! In this last video on linear algebra, I'm going to talk about the inverse of a matrix. But before we get to that, I want to um, just return to a quick example that I stumbled upon in the previous video, which was the rank of the matrix, the second matrix down here, excuse me, where we have a 3 by 3 matrix and it has the rank 2. And I said pretty straightforward that the third row is a linear combination of the first two rows. And I said, okay, if you add the first row to the second row, we get to the third row. Now, in principle, if three rows are not linearly independent, that also implies that the three columns of this matrix have to be linearly dependent. So one column is a linear combination of the other two columns, or can be written as the linear combination of the other two columns. And I didn't look at the example right before, and then stumbled upon it because I saw, okay, adding the first two columns, of course, doesn't result in the third column. But the statement is still true, and I just wanted to make sure that we all see this. The underlying problem, of course, is that if we add the first two columns, it's a 3, 4, 7 matrix, which is not equal to the third column. But they're still linearly dependent. They are linearly dependent because we can go through the math if we multiply the first column by 2 and multiply the second column by 5 and add those two together, that will be equal to 5 times the third column. So they're still linearly dependent. The rows are still linearly dependent. It's just not quite as straightforward to see as for the rows, where we can just add the first two to get the third row. So just to kind of confirm for yourself that this is also true, if we just look at the columns, just go through the math, multiply the first column by 2, second column by 5, third column by 4, and then you should get get the same result. So yeah. So the last topic, or second to last topic, the inverse of a matrix, and that's another important concept that we will mention many times when we kind of derive OLS using matrix algebra. Before we start talking about the inverse of a matrix, we have to talk about the identity matrix. And what we mean by an identity matrix is the following. It's always a square matrix, so an n by n matrix, denoted as IN. And it's the matrix whose diagonal elements are all ones, and the all off-diagonal elements are all 0. So here's a 2 by 2 identity matrix with ones in the diagonal and zeros in the off diagonal. Here's a 3 by 3 identity matrix, again just ones in the diagonal. All off diagonals are zeros, and you can think of this matrix as kind of the one. It kind of plays a similar role as a one in kind of scalar algebra with scalar numbers. Because if we multiply the identity matrix by another matrix, then the result is the same matrix. Okay. Then, if we know what an identity matrix is, we can also define the inverse of a matrix. First, we call a matrix an n by n matrix A. We call it non-singular or invertible if there exists an additional n by n matrix A to the power of -1, so A inverse, such that A times A inverse is equal to A inverse times A. So we can now switch around the order because the product of these two products, or these two matrix, the results of these two matrix multiplications are the identity matrix. Okay. And so if there is a solution where this A inverse exists, then this is the inverse of A. And there is no, if there is no such A inverse, if this doesn't exist, so no A inverse exists that satisfies this condition that the product is equal to the identity matrix, then A is called singular or not invertible. There are a couple of important properties of the inverse, and they're related to linearly independent, or the rank of a matrix and linear independence of the rows and columns of a matrix. First, in general, if an inverse exists, then it is unique, okay? Then second, if A is non-singular, so if A is invertible, then of course A inverse is non-singular as well, so it's also invertible, okay? Secondly, if we take the inverse of a matrix, we end up with the original matrix. So A inverse and the inverse of that is equal to the original matrix A. Next, if A and B are non-singular, so if both are invertible, then A times B is also non-singular. And if we take the inverse of the matrix multiplication A times B, we can kind of split this up, but we have to kind of switch the order. So that's equal to B inverse times A inverse. Next, if A is non-singular, so if it is invertible, then the inverse of the transpose of A is equal to the transpose of the inverse of A. So we can kind of switch around here the transpose and the inverse. The last topic is the determinant of a matrix, which we will encounter as well going forward. In general, determinants of a matrix can be used to determine whether a square matrix is non-singular, so whether it is invertible. In general, the determinant of a 1 by 1 matrix, A equals just the element A11. If we have a 2 by 2 matrix, then the determinant A is equal to the product of the diagonal elements minus the product of the off-diagonal elements, right? So we take the product of A11 times A22 and subtract A21 minus A12. And the important point is that a square matrix, and this can be extended to larger matrices, and the important point is that a square matrix is non-singular if and only if its determinant is not 0, okay? So by just checking the determinants, we can quickly determine whether a matrix is ultimately non-singular or whether it is invertible. I guess the last topic or the last thing to mention how this is related to the linear independence is that in general, every matrix, in order for a matrix to be invertible, all the matrix has to be of full rank, which means that none of the columns or rows are linear combinations of the other rows and columns, okay? And all this sounds very technical, but if you have used linear regression before and you kind of remember from linear regression that you can't, for example, include two variables that are perfectly collinear in one OLS model, or usually your statistical program would drop out one of those variables. The reason why that is the case ultimately is related to this issue of whether a matrix is invertible and to what extent one column or row is a linear combination of another column or row in that matrix. So it is inherently related to a lot of the topics that we will discuss later in the semester. So it's important to kind of make sure that you're, as soon as I start talking about inverses and transposes of matrices, you can kind of go back to the material here to kind of refresh your memory of what exactly conceptually is going on. All right, this is all for this week. I know it's a lot of math and a lot of different concepts, but I wanted to give us a broad overview, quickly go through kind of the key concepts, and we will refer back to them as we go through the remainder of the semester.